Hi everyone, my name is Christine Jacinto. I'm a high schooler at Lane Tech College Prep in the CDAC Summer Lab program. Today I'm honored to be introducing Dr. Rebecca Willett, a professor of statistics and computer science at the University of Chicago and a winner of the National Science Foundation Career Award and Air Force Office of Scientific Research Young Investigator Program Award. Dr. Willett has made a name for herself as an expert in the fields of machine learning, large-scale data science, and signal processing through her research in network and imaging science and applications in wireless sensor networks, social networks, astronomy, and medical imaging. Today, we'll hear Dr. Willett speak more in depth about her contributions to studying how data science and machine learning aids research advancements in physics, climate science, and other fields. So please join me in welcoming Dr. Willett to the Summer Lab Speaker Series.
Thank you very much, Christine. So first of all, can all of you see my slide? Great. Yeah, thank you so much for the invitation. It's really exciting to get a chance to talk with you all today. I'm sorry we can't meet in person and have more one-on-one interactions, but I'm still really happy to be able to tell you about one aspect of some of my research recently here at the University of Chicago. And this is work that I've been doing with my graduate student, Davis Gilton, and postdoc, Greg Anji. So in particular, we've been studying solving inverse problems in imaging. And this is a problem that shows up in many different contexts. So examples of this general problem include in painting, where there's a true image beta that we're interested in, but we only observe a subset of the pixels. So there's some missing pixels, which I've shown in black for Y here. And what we want to do is to fill in those missing pixels. Or deblurring, where there's, again, a true kind of crisp image that we're interested in, and we want to remove the blur from that image. Super resolution, where we want to take a low resolution image and map it to a high resolution image. Or various kinds of medical image reconstruction. So for instance, in MRI, we observe things like Fourier transform coefficients of an image. And from those, we want to reconstruct what the image looks like. So for all of these applications, we can think of them all within the same mathematical framework. So the idea is that what we observe, we're going to call Y. And this is just a collection of all the pixels that we observe. And we think about that as being related to the true image beta that we're interested in. And X is just going to represent the mapping from beta to our observations. So it would represent like the blurring process or the loss of some pixels. And of course, our observations might have a little bit of noise or some errors in them, which we represent with epsilon. And so our goal is to recover this image beta from Y, where we know what X is, but we don't know what the noise epsilon is. So this is something that you maybe have seen a lot in the movies or on TV. So I'm going to try, I've never done this before, but I'm going to try to play a video here over Zoom, and hopefully you'll let me know how it goes.
Lock on, enlarge the Z-axis. Enhance, freeze and enhance. The eigenvalue is off.
Okay, so I don't know how much of that came through, but there's just this huge number of different TV shows and movies where they'll see a really crappy image in like some surveillance photo, or they'll see like the reflection of a scene in somebody's eye, and they'll want to take an image and enhance it so they can see what kind of detail is there. And that's related to these inverse problems that we're discussing here. Okay, so in general, you know, the very first thing that you might consider doing would be to just find whatever image beta gives us the smallest errors or as close as possible to Y. So that would correspond to a least squares fit. So we just choose the image beta that minimizes the squared difference between Y and X beta. And we can use ideas from linear algebra to write down exactly what that formula is very easily and directly. So in this picture, can you guys see my mouse? Great, okay. So here I've got a blurry image of a guy with a camera. And in this case, in this first image, there's no noise. And so if I try to do this least squares solution or approach, then I get a really good, very accurate estimate. But the problem with this approach is that even if there's just a tiny bit of noise, so little that when you and I look at it, we don't see anything. There's just very tiny errors in this image. When we try to apply this least square solutions, we get complete garbage. It really doesn't work well at all. And that's because if you look at this formula over here, you can see that we're taking something that, I'm not sure how much linear algebra that you guys have had, but we're computing an inverse. And it's analogous to saying, I've got a number that's super close to 0, and then I'm taking 1 over that number. And so if that number is super close to 0, then 1 over that number is huge. So it's like we're multiplying a huge number times our noise, and that's getting added to our estimate. And so we get these really garbage looking results. And so what people do to avoid these garbage looking results is they'll use techniques called regularization. And one of the very first approaches to regularization dates back to the 1940s, where Tikhonov proposed a certain kind of regularization. So what he said was, what I'm going to do is I'm going to choose my estimate of the image, beta hat, by searching over all possible betas, all possible images, and choosing one which, first of all, is a very good fit to my data. So my sum of squared errors is very small. But also, I want to make sure that none of the pixel values in beta are too huge. So I want to make sure that the sum of the squares of all the pixel values are relatively small. And it turns out that this optimization problem is something that we can solve very easily. We can write down a nice little formula. And basically what happens is now, instead of taking 1 over a super tiny number, we're taking 1 over a reasonably sized number. And so we don't have this huge explosion of our noise. And when we look at the results, we see something that looks much, much better. So this is one of the first approaches to regularization, and there have been many since then, where people would say, well, let me try to model the geometry of images or statistics of images to come up with other kinds of regularizers. And what they mean by that is, instead of just looking at the sum of the squares of all the pixel values like Tikhonov did, let's try to come up with some other model of which images are good and which images are bad, and try to find good images that fit our data. So what I want to talk about today is what happens when we don't know ahead of time what image geometry we're looking for. So in general, we're going to consider a basic framework where we're going to say we're always going to choose an image estimate beta that minimizes our sum of squared errors to our observations and some regularization function R. And what we're going to explore is what happens when we don't know what the best regularization R to use is. And we saw in the Tikhonov case that the one that I showed, that his regularizer did well, but we certainly have room for improvement. And so what I want to explore is what can happen when, instead of choosing R a priori based on some kind of smoothness or geometric models, can we learn this function R from training data? So if I've got a giant database full of different images, can I use it to learn the best way to regularize images? And the answer is yes. So there have been a number of different papers that have explored this topic. And for the most part, they fall into 4 different categories. And I'm going to give you a brief overview of some of those categories today. So the first one that we'll talk about is what I call model agnostic. And the idea here is that they don't really use a lot of detailed information about X, this model of how our image was corrupted, because remember, our goal is to remove that corruption. So an example of this might be with super resolution. So we start with a low resolution image, And then we try to get up to a higher resolution using something that's just very simple, not really learned, not very sophisticated, just bicubic interpolation. And we get something that's a higher resolution, but kind of blurry, and there's some blocky artifacts. And then we would train a machine learning method, such as a deep neural network or a convolutional neural network, to basically remove all of those artifacts and get to a nice high quality reconstruction. So this is a reasonable approach for problems like super resolution, where we have some idea of how to do this first step, but it really doesn't leverage detailed information about the X, about this sort of corruption. And so this method doesn't work very well in a broad range of other kinds of inverse problems. So with that, I want to turn to a broader category that can be used in more settings, which I call decoupled. And the idea here is that there's two things we're trying to do. One is we're trying to exploit knowledge of X, or the corruption in our observations. And the other is that we want to exploit all of our training data that allows us to learn the structure of images. And decoupled approaches kind of keep those two things separate. So here's an example of this approach. So we said that what we were going to do was try to find an image beta that's close to our data and as a small value of a regularization function. So what we're going to do now is we're going to use what are called generative models, such as GANs, in order to tell us what this regularization function would be. So you might have seen examples of GANs on the internet or in the news where people will actually generate, say, images of people's faces that are not real. Like these are not people that actually exist. They're just being generated by some neural network model. And so I can actually feed in, say, some sort of random noise, a few random numbers into this model, and it'll produce a random but realistic looking face. So we're going to use this model in order to help solve inverse problems. We're going to say, what I want to do is I'm going to choose my regularization function to only select images beta that could somehow be generated by this GAN. And we're not going to allow ourselves to choose anything else. And the idea is that somehow the generative model somehow has encoded what makes a face look realistic or normal and what doesn't. And so the idea is that if we only consider images beta that could have been produced by this GAN, then we'll only be choosing, say, realistic faces or realistic images. So the idea is that once I've trained this generative model, then what I do is I choose whichever image in my generative model best fits my data. So this is a method that was proposed a few years ago by a group at UT Austin. And here's an example of this in action where they were trying to solve in-painting. And they used 80,000 samples or training images in order to figure out what this generative model should look like and then solve the inverse problem. So this looks very good and very promising. But the problem is that if I were to somehow use less training data, let's say 2,000, then this method completely breaks down. So this method is extremely sensitive to how many different training images I have available to myself. So a key question underlying all of this is how many samples or how many different training images do we need in order for one of these methods to work reasonably well? And if what we wanted to do is to be able to reconstruct images of cats, where there's millions and millions of images of cats on the internet, then maybe this isn't such a big issue. But there are many problems like medical image reconstruction, where it's a huge issue, where we don't have very many training images, where there's a lot of variety to the shapes of people's brains or the different kinds of conditions or tumors or lesions that they might have in their brains. And so the amount of training data available is relatively small compared to the complexity of the task. And so what we really need are methods that are going to work even when we've got a relatively small amount of training data. So this is a problem that I've thought about for many years. In fact, when I was a graduate student, I was studying image reconstruction problems. And I went over to the hospital associated with my university because they were doing a psychology experiment where they were having people do different activities in an MRI scanner and collecting what they call functional MRI data. So they basically wanted to see which parts of our brains were active as we did different kinds of activities. So I went over to do this because they said anybody who participated in this experiment and let their brain be measured would get a CD with all of their brain data on it, and I thought that would be kind of fun. But then they gave me a call a few weeks later and they said, well, we were looking at your data and we saw actually a giant tumor. And they said, you know, we only have an experimental machine, but you really need to go see a doctor right away. And so I did. I went and, you know, a few months later, I had it removed and everything's been totally fine ever since. But it's always sort of like ingrained in me this sense of how important these things are, and how important high quality images coming out of these things can be to people's lives. Okay, so let's talk about why this GAN approach is problematic, because by understanding why it's problematic, we can maybe understand how to do better. So in particular, one way of kind of thinking about the way that this GAN or generative model approach is working is that the generative model is somehow telling us, well, what's the probability distribution of all possible images? Or which images are likely to be good images of faces and which images are really unlikely to be good images of faces. So when we learn a generative model, implicitly, we're kind of learning what this probability distribution is. But if we think about a problem like inpainting, we're actually having to learn a lot of stuff about the images that's totally irrelevant to the inpainting task. Like if I want to fill in this woman's nose and eye, it really doesn't matter what color or the background is or whether she's indoors or outdoors. But when I learn this generative model, I'm forcing myself to learn all this extraneous information that's totally irrelevant to my task. So in contrast, you could say, well, what I really need to know is not like the full distribution over all images, but rather somehow the conditional distribution of the missing pixels given the pixels that I observed. And it turns out that there's a lot of theory and mathematics and statistics that's studied this problem that's shown that there's a lot of reasons why this green problem of estimating a conditional density can be a lot easier than the red problem of learning the full distribution. And in particular, it can require a whole lot less data. And so what this implies is that when we want to learn how to solve these inverse problems in imaging, if we know what X is ahead of time, we should be using it. Because if we're not using it, then we're definitely not learning this conditional density. And so we're more likely to need a whole lot more data, a whole lot more samples. Okay, so this brings us to the last two categories of approaches, unrolled optimization and Neumann networks. So with unrolled optimization, what we do is we say, let's just imagine for a moment that we knew what a good regularizer R is. Now, if we knew that, we would have to solve this optimization problem. We'd have to come up with a mathematical and computational way of searching over all possible images beta and finding the best one. And a classical method for doing that is gradient descent. So what I do is I start with some initial estimate, and then in each stage, what I'm going to do is I'm going to update that estimate. And the way I'm going to update it is I'm going to take the estimate from the previous round, beta hat k, say, and I'm going to push it in the direction of fitting my data better and in the direction of having a lower value of this regularizer. And I can actually represent this with a block diagram like I've done at the bottom. So I can input into the bottom some initial estimate, and then I go through multiple different stages And at each stage or block, I do two things. I push it towards being closer to my data, and I push it towards having a better value of this regularization parameter. And if I do this B times, then I've got this diagram with B different big blocks. So now what I can do is I can say, all right, well, now I don't know my regularizer. So what I'm going to do is I'm going to take this block diagram, and everywhere where I see the gradient of my regularizer, I'm just going to plug in a neural network that I can then train. So now what I have is this giant block diagram where some components in it are neural networks, and I'm going to train these neural networks in order to produce a good estimate on the output. And the nice thing about this now is that when I'm training my neural network, at each step of that training process, this model X is involved. So right from the very beginning, what I'm doing is I'm taking into account the nature of the corruption of my data, and I'm using that information to somehow optimize my neural network. And that's totally different from the other methods that we talked about earlier. So one of the things that I did with my student my student Davis and postdoc Greg, is we came up with a slightly different approach to this, where instead of starting with gradient descent, we started with something called a Neumann series. And it's kind of similar in that we take somehow an iterative procedure and we write it as a block diagram, and then we replace a component of it with a neural network. But there's a key distinction. If we do a side-by-side comparison of these approaches, what we see with this unrolled optimization or gradient descent approach is that it's kind of serial. Like my data, my estimate goes through block 1, and then it goes through block 2. It has to go through all the blocks before it goes to the end. Whereas the Neumann network, in contrast, has got these red arrows. So we derive this using mathematics, but it has this really nice feature that comes out of it, which is that my final estimate is the sum of all of the things coming out of all the individual blocks. And so if I make a small perturbation to this first block, for instance, my output notices it or senses it right away, as opposed to it having to go through all the other blocks before I see anything. So let's just look at some of these things in practice. So we talked about these 4 different classes, and now what we're going to do is we're going to choose one method from each of these classes and see how they work in practice. And we're also going to see actually a 5th method where we took this Neumann network and we made a small little change based on, again, the underlying mathematics that said, well, how do we optimize the input to this network and adjust things accordingly? Okay, so here's some pictures. So first of all, just a little anecdotally, we can look at this deblurring problem. And on the top 2 rows, we're seeing what happens when we learn how to do deblurring with only 2,000 training samples. And on the bottom, what happens when we learn how to do deblurring with 30,000 training samples. And so on the top, I've got the original image and the reconstructions for these different methods. On the bottom, I've got the actual observation, the blurry image. And these black and white images are showing errors. So the more black it is, the fewer errors there are. So it's a way of assessing how accurate these things are. And what we're seeing is exactly sort of the claim that I was making before, that methods that somehow use the forward model X, that use this knowledge of the underlying physical system, do a lot better than methods that just try to learn everything about it or don't pay attention to it till the very end. And this is true not only in this one little anecdotal example, but when we try lots of different inverse problems and lots of different training data sets. So what we're seeing here is the accuracy on the vertical axis as a function of sample size for these 5 different approaches. And we see that the Neumann networks are consistently the best by a pretty wide margin. Okay, so I'm about out of time. I just want to mention a couple of small things. One of the things that I hinted at earlier is that there's a lot of interest in using these tools in applications like MRI. And one of the reasons for that is that when we look at classical methods for reconstructing these images, I mean, I'm talking about the tools that are actually used in hospitals today. those require a lot of computation because there's no machine learning involved. And so I can get a reasonably good estimate, but it takes, in this example, 350 seconds. And in contrast, the other three examples here are all examples of things that were learned. And the first two correspond to the preconditioned Neumann network and the Neumann network. And what we can see is that these models require way less time, like 2 orders of magnitude less time to compute, and they're getting more accurate results. And so one of the reasons why this area is exciting is that we might be able to not only improve accuracy, but also get estimates or images much more quickly. So your doctor could maybe be looking at a scan of you, and instead having to wait and look at it later and then tell you the results, they can just look at it while you're lying in the scanner and adjust and decide where they want to focus next accordingly. Now, that said, there's still a lot of mysteries and unanswered questions in this field of research, which makes it especially exciting. So one of those is we are curious about what happens if we, say, train one of these systems for a scanner at the University of Chicago, and then Northwestern University Hospital wants to use the same method. So on the top here, I'm showing what happens if we train the scanner to work at the University of Chicago, and then we actually use it at the University of Chicago, and it works well. So this is basically what we've been talking about all morning here. On the bottom, what I'm showing is what happens if we train it to work at the University of Chicago, and then later on actually try to use it at Northwestern University. And what we see is that it actually decreases the accuracy. And the amount by which the accuracy decreases somehow depends on what algorithm we're using. And so one of the big questions that's kind of engaging this community right now is how to make these methods in a way that they're really going to work well, not just for one scanner in one hospital at one location, but so that they'll work over a bunch of different scanners, so that we can somehow adapt to new scanners at new locations. Another thing that is kind of interesting to this community right now is figuring out how to make sure that we're going to be able to do things like reconstruct tumors. So on a naive level, if you were to say, have a training set of MRI images where none of the patients in this training set have any tumors, and then later on we take data for me when I was a graduate student and there's a tumor, we wouldn't want the machine learning method to erase it and say that, oh, that's just some noise because I've never seen anything like it in the training data. And so a key question is, how robust are these different methods to things like tumors or other features that are somehow not in the training data? And how do we develop guarantees that we aren't going to miss anything important when we start using these learned methods? So thanks very much. I personally hope this was exciting to you. I think it's an interesting area with important applications. And it also allows us to bring in different tools from statistics and mathematics and computer science in a pretty exciting way. And we've got a couple of papers about this. The first one's a little bit more detailed about Neumann networks in particular, and the second one's more of a kind of tutorial about the field as a whole. So thank you very much, and I'd be happy to answer any questions.
Thank you very much, Becca. That was awesome. If you wouldn't mind, we might keep the questions until after David's talk so people can ask questions of both of you at the same time and get maybe the same or different perspectives. For the students out there, please, sorry, Becca.
I said, yes, that's totally fine.
Awesome, thanks a lot. For the students out there, it'd be great if you guys can note down the questions you have, think about questions for both Becca and David at the end of this, and we'll hand it over to Chinmaya now, who's going to introduce David, I think.
Yeah. Hi everyone, my name is Chinmaya and I'm a junior at the University of Illinois at Urbana-Champaign in the CDAC Summer Lab program. I'm delighted to introduce Dr. David Miller, an associate professor of physics at the University of Chicago and winner of the NSF Career Award in 2015. Dr. Miller's research centers around the interaction of fundamental particles like quarks and gluons using data collected from the ATLAS detector in the Large Hadron Collider. Today, he is going to be speaking more specifically about how data science and machine learning helps boost research in physics and science. I have the privilege of getting to work with Dr. Miller as a research assistant this summer, working on an interpretable machine learning model to gain new insights into the trigger system of the Large Hadron Collider, which is basically the data filtering system. And I'm excited for everyone to have the opportunity to hear more about the intersection between AI and physics. Please join me in welcoming Dr. Miller to the Summer Lab Speaker Series.
Great. So indeed, thank you to everybody, but most importantly, the students who are connected. And of course, also thanks for the invitation. And the introduction by Chinmaya was far too grandiose, but I'll try to live up to its high standards. And also Becca is an impossible act to follow, so this is all going to be very boring in comparison. Okay, so as Chinmaya indicated, I am actually a physicist. So I am squarely on the science, on the physics side of the AI and physics kind of marriage that has happened over the past years or decades, depending on who you talk to. And this beautiful image is actually the result of putting together two very disparate energy and length scales of the universe. Of course, the outer universe and the large scale structures that you see when you look up with telescopes into the sky, as well as the accelerator system, the particle accelerator of the Large Hadron Collider, which in many ways is the kind of telescope or microscope that we use as high energy experimental particle physicists to peer deep inside the universe into the fundamental constituents of matter. Before I launch into all of the lovely background, I actually, especially because of at least one of our students, in fact, the one who introduced Becca, I wanted to tell people that, you know, this journey wasn't very linear. I went to, I'm actually from Chicago. I went to Lane Tech, where back in the day we learned, you know, drafting and wood shop and electric shop. And I took no offense to Miss Stone, but a really terrible physics class, and was terribly unprepared for college. But somehow made it here anyway. And I think that at the end of the day, it's really the result of just getting really into the things that I was studying and working super hard. And none of this, I don't think, ever came naturally, but here we are. Okay, so with that blast from the past, we can, I think, get a little bit more focused on the context of the projects that I will describe and that Chinmaya introduced. And let's start with what I call, in this case, in this representation, the periodic table of fundamental particles. I took chemistry in high school. It was a very tough course, where we, of course, all learned about the periodic table of the elements. And if you think about the patterns of that table, they are some of the first hints of quantum mechanics. Right, the Pauli exclusion principle is what dictates the structure of the outer orbitals of atoms, and that's what eventually dictates what molecules and structures form. But of course, you peer deeper inside and you find that actually atoms are made up of protons and neutrons are made up of, in fact, quarks. So this top set of particles are the 6 quarks that we know of that exist. And then they have cousins, the leptons. You all are very familiar with the electron. It's what is powering my computer. It's what we use for all kinds of communication. And of course, you also know very well the photon. That's the light that is being generated by the screen on my computer and yours. as well as the sun and all sorts of other things. But many of these other particles we don't have a daily familiarity with. They are particles that are heavy, that eventually decay to, for example, or produce electrons or the quarks that make up the proton and the neutron, the up and the down quark. But we discovered that these exist by studying with the sorts of devices that I briefly showed you a picture of a few slides ago, and looking, like I said, at the fundamental structure of the universe and seeing that there is more than just the simple things that we see every day, just like there are more elements than carbon and oxygen and nitrogen, which are the ones that we are basically most familiar with on a daily basis. We can go even further and we can study all of the details, the masses, the interactions between these particles, and we can build a table that looks very much like the periodic table of elements that was probably on the walls of your high school science classes, just like mine. And one of the things that you'll note here is that we can categorize these particles into a bunch of different types of interactions, those that have the strong nuclear force or that interact via the strong nuclear force. And of course, those are aptly named as being the particles that are that participate in the structure of the nuclei themselves. And then there are also particles that interact via the electromagnetic force. And there you'll find at least a few of the ones you might have expected: the electron, aptly named again, and the photon, which is the force carrier. But there are many others. And the discovery of these particles and the fact that this is what underlies the particulate aspect of the universe has taken many decades. And I'm going to skip a lot of the details, but this all looks very convincing, perhaps, especially if we took the time to discuss exactly how all of this came to be known. But that convincing aspect of this picture is kind of belied by big open questions. And so if I draw a literal physical representation of the masses of some of these particles, or in this case, I drew it where the volume of these spheres is proportional to the mass of the particles that sit in the tables that I just showed you. You can see just some absolutely bizarre structures. And of course, had you looked at all the little numbers that are present in this table, you would have seen the same information. But this visual representation, I think, makes it super striking that even though we think we can build this very lovely table, just like we could with after Mendeleev's discoveries, the question is, why does it look this way? Why were we able back in the day to put the elements in that table? And the answer to that question led to quantum mechanics. And now we make this new table and we say, but why does it look this way? Why are some of the particles that exist in this table thousands of times heavier than others? Why do they group themselves into these groups of 6? 6 is a bit of a strange number. Why not 5? Why not 10? Why not something that was either, base 2 or base 10? Who knows? And so the question of why the universe looks this way is really what drives a lot of particle physics. But what you'll see in a second is that the tools that we are using to try to answer that very simple question force us to come to terms with a lot of the intellectual infrastructure that people like Becca have laid the foundations for, and try to use this to try to answer the questions that we're asking on the physics side. So just a couple to throw out there, although I'm going to spend a little bit more time on the project side of a lot of this work. Some of those questions are things like, can we explain dark matter, which likely many of you have heard of, or the possible existence of new particles? Are those new particles potentially the explanation for why we saw the patterns that I just showed you on the previous slides. And do we even understand how these particles that, maybe on a tabletop that is at low energy interact with one another when we take them to, approximately the speed of light and slam them into each other? Are there new dynamics, new interactions that appear? But to answer those questions, we need to ask, how do we even ask them in the first place? And one of the things I always tell friends who aren't scientists, or even young budding scientists like yourselves, is often the answers are the easy part. Asking the right questions and asking them in the right way is the hard part. And so that's what I'm gonna focus on. Not that I know the answer to those questions either, but we're certainly having some fun asking them. So this is the instrument that Chinmaya referred to, the Atlas detector. And in the Large Hadron Collider, as the name suggests, we are colliding particles, protons to be specific, and then they spray out from the center of these collisions, and we try to take pictures, basically 4-dimensional pictures, 40 million times a second. And we do so with one of the largest pieces of, kind of single apparatus ever constructed. If you haven't noticed by now, but the scale is provided in this image on the left by a pair of humans standing near the bean pipe, which is very ill-advised, but they're doing that nonetheless. And this effectively functions like a giant single camera. And therefore, many of the things that Becca just described start to apply. That is, how do we analyze the images? How do we even gather the images to be analyzed? How do we then pick apart what has happened in those images once we're able to process them? Just for fun, here's an actual picture. I didn't take it, but I was building the instrument around the time. But because of some dangerous things that were going on in the cavern, only a few people were allowed there at the time. So you can see this giant camera, essentially, inside of a gigantic magnet system. And gigantic, I think, is appropriate. You can see, again, now a real person, not computer generated, sitting down here. And actually this piece of instrumentation is called a calorimeter. You can see it's built up of all these different wedges, 64 of these iron wedges that have to get lowered into place. I actually took this photo. This is a team from Russia who specializes in the precise movement of large pieces of equipment. Each of these wedges weighs 15 tons and has to be manipulated to within a few millimeters. And this is me climbing around underneath the superconducting magnets of this instrument, plugging in cables when I was basically a technician back in the day. So electric shop at Lane helped. Okay, so we need to record the images from the debris left by these collisions, but as I said before, we need to do so in 4 dimensions, so we need the time component of all of this as well, and we have to do so 40 million times a second, or as fast as we can, close to that number. And so what you see here is, again, a kind of graphical representation of this, but now looking as if this were a kind of slice of the onion that you saw a minute ago when we were looking at the end of the detector. And you can see that the reason we have structured it this way, with many different individual pieces of instrumentation, is so that we can get different measurements from different particles that might pass through it, and then try to build that, kind of put that puzzle back together as to what actually happened. And so to just reference Becca's talk, this is like being able to take individual pictures of different parts of, let's say, the brain. For example, some tissue and then some blood, and then be able to put that back together, which is, in fact, what part of these reconstruction algorithms are doing for those MRI images, is you're trying to take a bunch of different measurements and then mesh them all back together and then present a graphical representation of that, that system. Now, one of the things that you're going to see in a second is that we can also kind of unroll this this instrument. Remember, it looks kind of like a cylinder. Let me actually just show you that again. So, you know, if you imagine, you know, the azimuthal angle or coordinate going around the circumference of this detector, and then the longitudinal coordinate along here being, you know, the z-axis of your cylinder, you can see that represented here, where you have the azimuthal angle on this direction, and then the kind of longitudinal coordinate, or in this case we use the coordinate eta, but the z-axis of the cylinder here. You can then project everything that happens, all of the measurements that we're making, onto that surface. That can be very useful. And one of the things that we need to do is kind of take that now two-dimensional image, although we can have many layers and kind of have an effective three-dimensional image at the same time, and start to analyze it for what has happened. The difficulty, as I said a minute ago, is that this is these images are being recorded, if everything is going well, 40 million times a second. And I challenge you, even with the you know, rapid mode of your iPhone or whatever smartphone you happen to have, to take 40 million pictures a second with effectively 100 million individual pixels. It's a lot of data. And so what that means is, if you think about how much time you have between looking at each of these images, we're talking order nanoseconds, so billionths of a second, to think about whether those initial images are useful. And I don't know if you're like me, but if I were able to take 1 million photos a second with my phone, probably one of them would be good. And that's the same when we were taking images of these collisions. Most of them are pretty much junk, not because the person taking the picture isn't very good at it, like me, but because the probability that something interesting happens is actually quite low. And that's what this graph on the left side here is meant to represent. So the things that are happening all the time are happening, you know, order 0.1 gigahertz. And the reason it's not 40 megahertz there is because actually multiple things can be happening in each image, which is a whole other set of issues. But you see some interesting things are happening about 1 million times a second. So 1 out of every 10 images, but we're actually not super concerned about that. Let's skip to the chase here. If you want to study the Higgs boson, these things are happening, you know, once every 2 minutes, which is fast, but a hell of a lot slower than 40 million times a second. And so if we want to study the Higgs boson, that means we have to kind of sift through the needle in a stack of needles, as I say, and figure out which one of those we're going to keep. And we don't want to lose it because it doesn't happen very often. So this is a huge challenge, both computing and reconstruction. And so we turn to our machine learning colleagues who have done fundamental work in this area over many years, and try to learn about how to take those techniques and apply them to the challenge that we're facing. Okay, and so one of the things that we're doing is building electronics with these ideas embedded in them. And so just to summarize, I'm going to throw a couple of different things at you. I'm almost, I think, out of time here. but we have, you know, a kind of amalgamation of instrumentation, algorithms, and ideas that are being brought to bear. And in fact, a lot of it is happening through CDAC. And as Chinmaya even introduced, he's playing a big role in the new ideas realm, which is a bit of a wacky concept, but so far, actually, he's demonstrated that it might actually work. Okay, so just very quickly, I mean, one of the things that we're trying to do is filter the data coming in. So here's an image that you might see. Of course, it's been, you know, graphically massaged and represented to us of the, let's say, charged particle trajectories that are being created inside the collisions. And one of the things that we want to do is filter this data down to something that is manageable but useful. And so what we're doing is we're making use of some rather novel electronics components. And this is, again, supported through CDAC, which is on a dedicated board, an electronics board that, in fact, I was in the lab all morning trying to get to work. And run both high-level and very low-level processes all at once on this. I'm going to skip this slide. What it is meant to show you is that you can take this image that I mentioned earlier and unroll it and actually see individual pieces of information on it that have structure to it. I think that's the primary message that I want to get across with this slide. And we're doing that, let me just skip to this, with this chip called a system on chip. So this actually sits inside your phone. There are many different types of these, but both iPhones and Android phones have these system on chips in them, and they combine GPU and CPU type processors, as well as something called an FPGA, a field programmable gate array. And what each of those different chips is really good at doing really one type of calculation. GPUs are better at certain calculations than FPGAs, and those are each both better than CPUs at certain computations. And when I say better, I really mean extremely fast and robust. Which are critical for processing these data in real time. And so we're taking that, and we have working with colleagues from Fermilab, but also several students, undergraduates and graduate students here on campus, at basically porting the sorts of convolutional neural networks that Becca even described in her research onto these devices and using them to process these data in basically hyper fast pace. And so what you can see here is a text didn't come out on that, but what this says is proof of principle embedded neural network on this electronics board that you saw earlier. And this is Emily Smith, a graduate student in my group, and she actually implemented a network that Becca already described, or at least referenced, called ResNet, which is an extremely complex network, in this case for differentiating between different types of pictures. And you can see that running on our board, it was able in very low latency, although not as low as we need. This is 230 microseconds. But if you go back up here, if you want to keep me honest, what I said was that we needed essentially 1 microsecond latency. And with a smaller network, we're able to do that for the aficionados out here. But in any case, it correctly, let's say, identified this picture as being that of a jaguar running on this board that Emily is standing next to, which was a lot of fun. So just to wrap up here, I only focused on this one idea of using these novel electronic systems to execute these sophisticated machine learning algorithms, but we're really involved in several things that all come together in this area. Chinmaya already mentioned it. That's actually the last bullet point here, sort of intelligent and interpretable trigger design. But in addition, we also have totally new networks that implement Lorentz symmetry group structures, and actually scalable systems and hardware acceleration that I kind of hinted at already. And this is working with people across the board in computer science and physics. Oops, I don't know why that animation didn't quite work. So in summary, we have a diverse set of approaches to exploring the particle universe, and also a similar diversity of people that are helping make that happen, which at the end of the day is really the beauty of the work that we get to do, is interacting with so many great colleagues. So I think that's it. Apologies for going a few minutes over. Thanks.
Wonderful.
Yeah, so all these machine learning models are like, especially deep learning models, are very difficult to understand, right? So how do you reach like a level where you start to trust the output of the model?
David, do you want to take a first stab, or do you want me to?
Yeah, I'm sure. I mean, we have the, let's say, benefit, although it's not always easy, in particle physics of having, of usually having some fairly robust model of the, let's say, ground truth, right? So we often have detailed simulators at a variety of levels. We often have the ability to take what you might refer to as calibration data or control data against which you can test things. However, so we're often able to constrain some dimensions along which a particular machine learning model, or just to use a cynical term, some black box model might go wrong. So we might be able to say, I can demonstrate that this particular issue is of little concern. However, the fundamental point of what we're trying to do is to ask questions that we don't know the answers to. And therefore, you will inevitably, if you're doing something, I would say, right, end up in a situation, whether that means region of phase space or a model parameter or something else that you have not explored and don't have a mechanism to constrain, and then you will be faced with this question. And so the ability, and this is why the work that I had mentioned about using symmetry group structures is so interesting to me, because if you can relate parameters or aspects of a black box model, and therefore make it not black box, of some machine learning model, to a fundamental physical parameter or feature or structure inherent in the system that you are probing, I think that can generate a significant fraction of the confidence that you would want to move forward in using that model.
Awesome. Thanks a lot, Becca. Did you have any quick final thoughts? I know you have to run.
Yeah, I mean, I think I totally agree with everything David said. And I think that, that's one of the exciting parts about using these tools in the physical sciences, where we actually have fundamental principles that we can use to kind of guide our understanding of what these networks might or might not be doing. And we've got ways of generating different kinds of tests based on our understanding of the physics that help us validate these models. But in general, this can be very complicated. So here's a little toy example, if you guys can see my shared screen, where, imagine that we wanted to train a machine to be able to distinguish between cats and dogs. And we generate a training set, or we collect a bunch of data and we split it up into a training set and a test set. But it just so happens that all the cats are indoors and all the dogs are outdoors. And so obviously this would many machine learning systems would learn whenever there's a bunch of grass, and I should call it a dog. And of course, this is a fallacy. But we would never really identify this off the bat just by looking at how good our training error is, or even how bad our holdout error is, or our test error is, because all of our data, has this this bias to it. And this is not just a toy problem, this is a real effect. People were trying to identify whether a chest x-ray had signs of pneumonia or not. And in that case, again, there turned out to be these sort of spurious correlations with things that had nothing to do with pneumonia that totally fooled the machine learning system. And yet, this is much harder for a human to look at the database and identify whether there's a problem with the training data. And so, trying to figure out whether, even basic things like, is our training data diverse enough so that I can trust the way that this system works is very hard to do. And there's other complicated things as well. So there are issues such as, people think about, can they design neural networks so that they're somehow interpretable? So we'd like not only for the network to give us a good prediction, but we'd also like it to say, I predict this chest has pneumonia because of blah, and we'd like to know what blah is, right? So some people are researching that. There's also been research on, ongoing research on some of the theory of deep learning. So with some of these neural networks, they're extremely flexible. So they can perfectly fit almost any data set you give it. And usually there's multiple different configurations of the neural network that all perfectly fit the data. And so some theoreticians are trying to understand, how do our training procedures for these networks prioritize one model over another model? How are those choices really made? And if we can understand that, then we might understand sort of more about what's going on under the hood, and that could help us develop some trust. But the short answer is, right now, I would say we can't really trust what's coming out of these things, except in situations like David described. And that's where a lot of ongoing research is focused.
Awesome, thank you very much. I love that we've got, we come back to a common theme in this program of distinguishing cats from other objects. So I just wanted to quickly say thank you again, Becca and David. We really appreciate you guys spending some of your time and sharing your research with us. For the students out there, if you're interested, there were a bunch of links there that you can follow up and read about other work that David and Becca do, and I'm sure you could shoot them an email and ask them a few of the other questions that you might have on the top of your mind. So thank you again, guys. We very much appreciate it.